Hello, welcome back. So we're doing lecture 7 today, and I'm going to share my screen right away. Okay, so we have the RMD file that is to be downloaded. I am knitting right now the file. Please also note that next week there's going to be the exam. The exam will be online for the period of 5 days. You have one attempt on it. It's timed. And I urge you to prepare, please, for the exam. It's not straightforward. It will require you to know the material fairly well. So we have today quite a busy schedule. We will be talking about RCTs and linear regression in the context of RCTs. We will be talking about how to analyze RCTs, why confounding in the context of RCTs is important. And also note that research note 1 is being assigned today. And we will talk about this in the end of our lecture. And looking at the syllabus right now, I'm seeing that we're making good progress. So I'm recording this a little bit in advance, but by the time this is being posted, it's already 10:18, no, 10:11, sorry. So we are progressing now with our lectures from, oops, so we're coming now. Last week we talked about statistical inference. Today we'll talk about, so we're reviewing linear regression that you're prepared for the exam. We'll be briefly talking about covariate handling in RCTs, speak about block randomization design and why this is important to keep in mind when planning your analytical approach. We will talk about the nature of observational studies and how they're different from randomized control trials, and we will get a brief overview of the research notes. So essentially, some of you have asked for a quick review of the material prior to exam 1. So please consider this today's lecture as this review. I'd be happy to come on at one point if there are specific questions, but I will be traveling for the next 2 weeks, so I will have limited availabilities, and if availability is probably very early in the morning. But in principle, I'm happy to come on. If there are really specific questions, some of you want to talk about some aspects of it, I'm happy to come on. And yeah, so this is this. So this hopefully will be created soon. I really should do this before I get out of classes. Okay, so we have here class 7. This is building up right now. Oh, that's all right. No, it did not. So the knitting takes a little longer for this class, obviously. Okay, here we go. That's done. So if we look at the slides now, let's get started. Okay, so this is class 7. We will be talking, as said, about linear regression review. We will speak about modeling purposes, estimations using ordinary least squares and maximum likelihood. We will talk about the inference, we'll talk about the interpretation, and the types of covariates that can be used in the models. We'll talk about model diagnosis, which we discussed last week, which is important to keep in mind for all purposes. We will be talking about different study types. So we'll be briefly talking about RCTs and handling of covariate in RCTs, and we will talk specifically about block randomization design. We will further talk about observational studies, why and how are they different from RCTs, and then we will gain a research note of one overview, and then proceed to lab 1. So the linear regression as a review. So we have the model basically discussed quite in detail. So basically the idea is to have a yi that essentially is on so the yi is on the left hand side. On the right hand side we have the covariates, which essentially is beta 0, an intercept. We have slope beta 1 multiplied by the x1, which essentially is a random variable, any random variable. Then we have essentially as many coefficients as we have additional covariates. So this goes up to a maximum of p. And we have in excess to that, we have the residuals, that is basically unaccounted factors, and the error that comes from measurements or whatever unaccounted factors may come into place. Of note, we are assuming that the left-hand side is not perfectly measured, whereas the covariates on the right-hand side are perfectly measured and as such reflect the left-hand side. So the error on both sides is only being taken into consideration with different forms of regression analysis. So essentially we have I equals, so I is the individual in participant or case that goes from I to n, which n stands for the sample size. We have the residual error, which is independent and identical invariant. We have then this error distributing in the shape of a normal distribution around the mean of 0 with a variance of sigma squared. We have yi is the sample, response, and dependent. So it's a respondent variable, it's a dependent variable. It can be blood pressure, depression score, you name it. It is a continuous variable. This is important to keep in mind. We have xki. X essentially are covariates or random variables that are being included as factors or predictors into the right-hand side of the model. We have with beta, we have the regression coefficients. A beta 0 is labeled as the intercept. A beta k or a beta p is essentially considered a coefficient that constitutes the slope for xki, which essentially is x as independent variable or random variable that is being included. And k as the number of factors is ranging from 1 to p. The beta is unknown and needs to be estimated from the data and becomes then the beta hat. EI is the aforementioned error term that has some assumptions on it, which are important for you to know. So please keep them in mind. Sigma square is a constant variance parameter, is also unknown and estimated from the data. We have a model that essentially builds as shown on the previous slide. The purpose of this is really the adjustment for confounders. Confounders is by the definition, these are variables that associate with the exposure as well as in the outcome, are notably not on the causal pathway. For example, SPP can be beta 0 as the intercept plus beta 1 multiplied by the serum glucose plus beta 2 multiplied by the H plus the residual error. To get a more accurate estimate of this beta 1, which constitutes the effect between serum glucose and SPP, we're adjusting additionally for the confounder H. So this is taking into account confounder. But now in addition to that, there's also the possibility to add additional variables, and then we're basically coming closer to actually aiming to predict what blood pressure will be for one particular individual. And this can be done by basically holding and fitting the model towards the participants in your population of interest. So you can extend the number of covariates and you include, in addition to age, you also include age squared, because you assume a nonlinear relationship. You include gender, you include EDU D1 and EDU D2, whatever you think is important to essentially increase the accuracy of your estimate. So notably, by increasing the number of predictors, we have substantially increased the R-square, which is defined as the ratio between the explained variability over the total variability. And in the context of increasing the R-squared, increasing the number of predictors, we have to be very aware that overfitting is a great danger of this approach. And for that very reason, there are adjusted R-squares, and there are various things to keep in mind in this regard. So there's, for example, in epidemiology, there's a strong tendency to go for minimally adjusted model, which is particularly with adding additional predictors in our times where we have so much data from all walks of life, from all aspects of analysis. We have to keep this very well in mind. So the model designs as stated above. We've seen that on the last two slides. The least square, which is essentially the fit of the model, will essentially follow to minimize the sum of all deviations, all squared deviations, and that will allow, and this is what we're seeing here. So it's yi minus x beta will essentially squared will essentially as the sum. We want to minimize this to the maximum. And for this, we're doing that for the reason to get a better head, which essentially is then the estimate of regression coefficient, where essentially then this beta can be used to essentially use for the prediction of the individual case based on that developed coefficient. An alternate approach to that is the maximum likelihood, which essentially aims to, on the inverse, maximize the log likelihood to essentially get as close and as small of a residual as possible. So we essentially are having the log of the product of yi minus x beta, and essentially this product is meant to be maximally fit this density function into the data at hand. So essentially we are then building this by building the product from I equals 1 to I equals n. Logarithmically transforming this will essentially allow us to estimate and quantify and maximize the probability. So linear regression review. Further. So I hope there's, so I encourage you for this particularly rather complex issue to also revisit the lecture, the respective lecture to discuss this topic. So we are essentially coming to y hat I as the predicted outcome, and we're defining the residuals here as the epsilon hat I equals Ri, or the residual I, where basically the residuals are quantified as yi minus y hat I. And this ranges from 1 to n again. So essentially we are getting residuals for each participant or each case in the population. So examine now the epsilon hat I with I to n to check the normality and equal variance assumption of epsilon I. This can be done by histogram to plot out the actual errors, by QQ plot or by plotting the predicted outcomes versus the residuals, which essentially also will allow to test for homoscedasticity. So we're pursuing now a null hypothesis that beta 1 equals 0, and the alternative hypothesis that beta 1 unequals 0. So where x1 is structurally related with y. We're constructing t statistics around this, where we basically build a difference between beta 1 hat minus beta 1 divided by the standard error of beta 1, but the standard error of beta 1 is basically based on the residuals. And the null hypothesis being true, capital case T equals lowercase t, DOF, where DOF is n minus p minus 1, which constitutes the degrees of freedom. So the p-value is then basically estimated based on the probability derived from the t-score, which essentially is calculated mainly from statistical software. So we are essentially assuming 5% as a usual threshold for statistical significance. So to continue, we're having now again the same scenario, but this time it's not a categorical variable. This time we're focusing on a continuous variable, and we have here BMI and age. So considering this for BMI, we get a beta 1 hat of 1.4 at a p-value of 2%. So now essentially you can say that BMI is significantly related with blood pressure at a p-value level of 2%, where a 1-year increment of age relates to 1.4. Where a 1 unit increment relates to 1.4 millimeter Hg increment of SPB. So okay, so I just cut this one. This is not 1 year. This is 1 kilograms per meter squared. I will correct this in the final version of the slides. I'm actually going to do this right now. So obviously we can, but this constitutes that we need to hold age constant. So this is important to keep in mind, because essentially beta 1 hat, as stated here in this example, with a 1 unit increment. Okay, I'm holding age as constant. Constant. Okay, good. All right, so back to this. Okay, so this is changed time, and there was also something else that caught my attention. Okay, back at it. Yeah. Okay, so increase of 1.4 millimeter Hg with 1 unit increment of PMI, which is kilogram meter squared. All right, next. So now we have categorically polytomous categorical variables. There, in the context of these, we discussed non-high score versus high score, with college here in this context, with college as the reference. Given that gender is being held equal. One typical way of how this is being phrased in publication, you find with all else being equal. So as an example, and you can play this example through, if you have a beta hat 1 of 5, you would have a p-value of 4%, a beta 2 hat of 2, you would have here, yeah, so we have made this example and we have run this example, right? So EDU is now marginally related with SPP at a p-value level of 6%. Holding chain the constant, non-high school graduate tend to have 5 millimeter Hg higher SPP than those graduate and colleagues, and this difference is statistically significant at a p-value of 4%. High school graduates tend to have 3 millimeter higher SPP than those graduating from college, and the difference is not statistically significant at a p-value of 0.4. So this is the interpretation of what you're looking at here, and with an overall p-value of 6%. So if there are any further questions concerning exam 1, please open discussion board entries. If there's anything that I think needs to be discussed in a further video, I can post a video explaining some aspects of it. I also can schedule within a limited framework of availability for the next 2 weeks, unfortunately, but I'd be happy to schedule one-on-one sometime early morning EST. Keep me posted, let me know, reach out to me. I'm happy also to do smaller groups. Let's try to schedule it. All right, so good. So this was this. So RCTs will not be part of exam 1. However, it is part of the overall curriculum that will be taught in this class, and we will be talking about this today. Okay, so you likely have heard already in the context of other studies about some basics of RCTs. This course essentially approaches it a little bit more from an analytic angle, and you will be learning some of the aspects that are pertinent for analysis of RCTs. So you know in principle what an RCT is. It's basically a 2 arms or multiple arms trial that essentially is conducted to compare these two arms. Randomization is basically a randomized assignment to receive either drug or placebo in this context of a drug placebo trial. And yes, so there's a reason why this has to be randomized, and we will talk about this. The reason, just briefly right now already, is to keep confounders balanced between both groups, therefore be able to draw inferences that essentially also establish causality more than usually possible in observational studies. So why is it randomized? Randomized is clear now. Controlled means that the trial has a control arm that means to essentially subtract the basis amount of effect of either the other drug or the placebo or whatever you're comparing it to from the overall trends in the RCT over the time. So you essentially, the only thing you get and you're interested in is the difference between the control arm and the actual intervention arm. And this is labeled the so-called treatment effect. So the trial is conducted to avoid chance to dilute the interpretation of the outcome due to treatment assignment. So we're trying to take out all confounding effects. We're trying to remove effects that could occur by essentially, so when you have an outcome, this outcome could be caused by probably several other reasons, right? So an example I like to use is, for example, so you wanna, so you have a depression score, and you want to compare this to a depression score in those that do exercise versus those that don't do exercise. So now if you have a large group that you split now and you're putting them in both arms, and you essentially, they all start doing exercise, or you just let them be, or you give them all access to an exercise program. And once you give one group access to an exercise program, the other group you don't give access to an exercise program, and you measure after the period of a year, you try to compare the depression scores. you will more likely have a stronger effect in those that have access to the exercise program. So however, if you're diluting the effect now by basically picking a group of in the control group of people that are, I don't know, more likely to do yoga, more likely to already have exercise, or a bunch of marathon runners, you create a disbalance in terms of the baseline criteria, the baseline characteristics. And by that, you will minimize the treatment effect. And by that, you are, to some extent, you are more likely to run in a type 2 error in the interpretation of your intervention, in the effect, efficacy and effectiveness down the road of your intervention. So this is essentially what you want to do. So the control group is actually super important, and so is the randomization. So essentially what you're doing is you mean to enroll your subject into your trial. And then the first thing you will do, you start comparing your control and your treated group. And so the example we're working here is lung cancer. So we have lung cancer outcomes, and there's obviously an obvious confounder in outcome observed in both groups is the proportion of smoking in the group. So if you randomize them between both arms, you are supposed to essentially have a balanced proportion in smokers. And that seems to be reflected by, I'm not sure in this one, but this would be one particular confounder in lung cancer studies. So the HELP RCT here basically shows the difference in link status, and essentially the shape and form of this table is a very classical form and depiction of a so-called table 1. And table 1 is always this table that you see in every study, and this is basically the table that provides you with demographics. And in the context of RCT, is super important that you basically show the baseline demographics that essentially are important and relevant for your investigation into the outcome. So the idea is here to really eliminate all other possible attributions of outcome differences, which should be confounding and selection bias. Well, selection bias would essentially, with good randomization, be randomized out. So selection bias would be, for example, where you have individuals that have characteristics that are not generalizable. And if you still are able to randomize them effectively, you hypothetically may have a non-generalizable crowd, but the selection bias per se would be less effectively acting as a collider. But this is, I leave that for the epidemiology classes, and this is for this class, I think the main aspect to be understood is confounding. The interesting aspect of an RCT is, as opposed to an observational study, because of this randomized allocation to the groups, and the comparison to a control group that basically dilutes this baseline effect of all included out and allows you to subtract this treatment effect from a control group and really find the true treatment effect attributable to the intervention, essentially allows you in the bigger picture to draw causal interpretations, causal inferences. In observational studies, you cannot really do that. Although those of you who remember this from epidemiology, you should have done this in EPI, intro to EPI. There are the 11 criteria from Hill that essentially will allow you to some extent get close to kind of draw causal inferences. But generally, all causality from observational draws is to be taken quite cautiously. So it is from RCTs. I'm not even saying this is 100% thing, but so there's really no certainty, and that's the beauty of science. So there will never be certainty. The only certainty you really can get is nowadays, I would say, like with meta-analyses, good, well done meta-analyses, you probably get as close as you can get. But again, there you have the same issue, because then you have heterogeneity of the study outcomes. There's tremendous variabilities in many of the study sets. There's again uncertainty, even if what is considered most certain. So, all to be taken a little bit cautiously. So causal interpretation is, take it as what it is, take it as the closest we can get to causal interpretation of data. In a perfect world, with a perfectly conducted RCT, you could analyze an RCT using basically a two samples t-test. Yeah, hypothetically, yes. In terms of regression, this would be nothing else than the model that we already have discussed and we're already quite familiar with. So we have an xi, which is either 0, or an xi, which essentially constitutes is a representation of the intervention arm. Let's walk away from drug. Let's call it intervention. It's really control and intervention, because this intervention could be anything. So I'm also teaching undergrads in psych, and like the examples, they are totally different. So you have an RCT is really done in all kinds of settings, and I think drug is easy to kind of comprehend, because you give a drug, you have an effect. You don't take the drug, you don't have an effect. It's easy to comprehend, but you really, if you think more globally of it as an intervention, I think it makes it easy and kind of preps you ready for down the road where you use it in different contexts. So usually you don't have to adjust RCTs. Reason for that is that an adequately powered, adequately sampled RCT should hypothetically have no disbalances between the groups. It still happens, it's still a problem. It's not that this is a 100% thing that will happen always in the right fashion. There are still disbalances, you still will find them, particularly with some certain designs. It's important to keep in mind, because when you, for example, you study blood pressure drug, or in my world, it's dialysis clinics, right? Or it's for drug, it could be doctors' offices or hospitals or a hospital network providers, so whatsoever. Everything that distinguishes one entity from another entity, and you have one consortium that recruits, another consortium that recruits, countries, different regions, everything that is kind of a distinguishing entity. Let's put it that way. I'm not sure I could think of a better term, but it's something that kind of creates something that is inert, but is in its holistic view several inert of these centers. So this can be many things. A classic example is here the example that Professor Sang is stating about Fisher and his agricultural comparisons, where you basically look at the crop varieties on 5 different fields. The conclusion of what I'm trying to say is, like, you have blocks, you have these units, experimental units. And while you may have within your block full exchangeability, and you essentially you have a balanced kind of outlook, this could be all difference between the blocks, right? So if you, for example, you have 5 different blocks, and then suddenly in one block, less people, and there's a certain composition in one block, and there's a certain composition in another block, and like there's a certain demographic distribution, there's a certain, I don't know, whatever feature you could think of, and demographics being the most commonly cited one. You have these blocks that are then balancing within itself perfectly, but amongst them all, there may be disbalances. particularly when it comes to blocks that don't fulfill the recruitment targets or whatsoever. It's like, or you gotta take everything into consideration. So this creates now something that is called an inter-block variation and an inter-block variation. So just as a recap, intra is always within, inter is between. So intra-block variation given, inter-block variation different and large. So you can apply block randomization. That means that you randomize on a block level and you have within the block a perfect randomization, and then you put them all together and you basically do the analysis. So this is block randomization. So this block factor is supposed to be a natural covariate, like for example, the agriculture data in Fisher's data. And here is the example of penicillin production. So it is important to keep in mind that all of this essentially matters, and you need to understand each part of it to essentially draw inferences out of this. So this was the Fisher agriculture data, and this is the experiment that he did to do. And it is basically around the penicillin crow. So he designed it as follows. So he basically created a raw material, corn steep liquor, that could be quite variable and only made in blends sufficient for 4 runs to those treatments. Thus, a randomized complete block design is definitely suggested by the nature of the experimental unit. So the data below was what Fisher found, and I'm posting in addition to that the Faraway paper, where you can read up on this data. So when we are fitting now a regression model that basically contains this block as a covariate, essentially will allow us to get a G. And this G essentially allows us to see the differences between the blends. So now we have here treatment and yield. We have A to D, and then we have blends that basically shows differences in the yield. The residuals here basically are shown, and they are somewhat heteroscedastic. And also when we look at the QQ plot, it looks kind of like nicely distributed. So now we have here the analysis essentially is the same as we have done it in the past. And it basically shows again this nominal kind of categories, and it shows the differences between the reference group and the respective treatment group. So we have treatment A as the reference, we have treatment B is 1 unit larger, treatment C 5 units, and treatment D 2 units larger. If we look at the blends, we also see that the blends also have significant differences, and these significant differences are here reflected with the p-values. We likely see that blend has here significant differences, while the treatment may not have any difference. So it's interesting to see. And then we have something which you still remember from introductory statistics when it comes to multiple testing. You can essentially test in the context of multiple testing, like this clearly is. You basically would show it by depicting Tuckey's pairwise 95% confidence interval, which is basically then also what you can quantify using Tuckey's honest significance testing. So none of these treatment pairs are essentially significant, while the blend essentially is here significant. So blend 5 minus blend 1 turns out to be significant. But back to general cases. So now this was a very specific example. So let's keep it simple. So other than blocking or the stratification and the chance of imbalance, there's no need to control for other covariates. So control meaning adjust for other covariates in the model. So if we supposedly know X2, which is the smoking, and we know it's impacting the outcome, we can add it to the model, but we don't have to because it does make a difference in terms of the estimation of the beta 1. So if beta 1 is here the intervention, and we include beta 2 that is equally balanced between those groups, it doesn't make a difference in greater run. The only downside, it also doesn't make a difference. It also doesn't have a downside really, but it will just not have an effect. The only downside could be that you're overfitting your model. So in fitting equation 1 would be the same fitting equation 2. Since x1i and x2i in equation 1 are independent attributes essentially to the randomization. So we do really not need this additional covariate. So in principle, x1i and x2i are independent if the correlation between x1 and x2 equals 0. So where where COR is basically the correlation coefficient. So if there's no correlation and the correlation coefficient is 0, which by its own right is not often found, so then there is really no need to adjust for this. So if we are looking now back at the HELP RCT, we can investigate the structural relationship between homeless and depression. We know that gender may also affect depression, and meanwhile gender might affect homelessness. Because the data is observational, homeless and gender is not expected to be dependent. That means that the correlation homeless and gender is unequal to 0. The primary outcome is status of linking to care. And so this can be randomized, but is not randomized because it's an observational driven. So we need to control for this to account for gender sufficiently. So depression of beta 0 plus beta 1 homeless and beta 2 gender, if we are omitting gender, the model looks entirely different. So this is a biased estimate, which basically will change the assumed effect of homelessness and depression. So note the E asterisk represents now gender and the error in equation 3, when the model in equation 3 is actually the true model because gender needs to be taken into account. So essentially E asterisk will actually be larger because gender actually had an explanatory effect on the model. So this is important to keep in mind. So not only the slope will change, also the error will change. So essentially what you can do, you can also assume that beta 1 is equal to beta 1 asterisk, which is of this newly non-adjusted model, which we see in the third down here, minus beta 2 multiplied by the correlation of x1, x2 divided by the standard deviation, the sigma of x1. So you can arithmetically estimate what your beta 1 will be. And this is important knowledge when you think about it, because by that you can really estimate what effect can be attributed to that included variable. So when we have now an unadjusted model, we have y equals beta 0 asterisk plus beta 1 asterisk x1 plus the error, the residual error asterisk. If we're taking now the beta 2 out, if we are adding the beta 2, by the estimate of this beta 2, we basically can now beta 1 equals beta 1 asterisk minus the beta 2 and the correlation coefficient of x1, x2 divided by the standard deviation. So therefore, we have the correlation of x1, x2 equals 0 will imply that beta 1 and beta 1 asterisk is the same because this drops off, right? This becomes 0. as a division to 0, and the coefficient multiplied by 0 is 0, so this drops off, so it stays the same. If beta 2 equals 0, then beta 1 and beta 2 is the same. So x2 has no impact, no adjustment is needed. So if beta 2 is now greater than 0 and the correlation of x1, x2 is greater than 0, so we're having now an increasing effect. Our beta 1, this guy, will be smaller than beta 1. So the direction goes in that direction, that part of this beta 1 asterisk will basically be reduced by an increase in your beta 2. The other way around is when beta 2 is greater than 0 and the correlation coefficient is 1. So this is where it becomes an additive model. So multiple regression is an additive model, meaning that beta 0 greater than 2 and the correlation smaller than 0, you have a lowering effect on your beta 1 asterisk. And by that, you essentially have a greater beta 1 than a beta 1 asterisk. Make sense? And then a few remarks on association and causation. So again, statistical association does not prove the hypothesis of causation, but we can examine if the data are consistent with the hypothesis, just lend support to the hypothesis. And this is a nice terminology, which I would very much like for you to memorize. It lends support to the hypothesis, the alternate hypothesis. Support from a greater amount of and more diverse types of data in different population increases the possibility of causal hypothesis. And this is the point where I will encourage you to go back to Hill's criteria and study these 11 criteria. There's also a very good publication out there. I actually am going to add this. I'm going to add this to the video. This is very, and I have this. It's a really good review actually on the tab. So one of the major things of this is like observational study lives and dies with replication. If you can live, if you can replicate findings in different population, different settings, slightly different research designs or analytical approaches, and it yields the same result, then causality becomes more practical, which is one of his criteria. All right. Okay. So quickly about confounders. It's not. Yes. So there's a common association of a third-party variable, a third variable, which here in this context here could be gender. So gender associates with education. I don't know. Females are more likely to go to college. College students are more likely to watch their BMI and to go on a treadmill, to do exercise. I don't know, to be more active, physically active. I don't know. It's like these are all the associations that are possible. I'm just making this up as we go. And also gender is known. Females are more likely to have higher BMIs for anatomical reasons. So hypothetically, this could be the framework you're looking at. So these are the directed acyclic graphs, which you will definitely do quite detailed in epidemiology. But yeah, so these are the associations you kind of could think of, and these confounding factors you're trying to kind of take out of your estimates and produce a more accurate estimate with your regression analysis. In addition to that, you have mediators, and mediators are different. So as you can see here, so education doesn't cause gender, right? However, if you have something that essentially will affect a third variable, this third variable in turn will affect the outcome. So education causes exercise, and exercise causes BMI. There is a mediator because it lies on the causal pathway. And this is important to keep in mind because these, per definition, you are not supposed to adjust or quote unquote adjust for. You need to account for them differently. And this is, you would start off with stratification, and then you can go into the realm of bivariate analysis. So they are quite fancy methods, so you can approach it. But basically, it would be stratification. Subconsequent, this is education causes BMI, BMI causes diabetes status, and diabetes status causes general health status. Again, you would not adjust an outcome for why. You would basically always go for the source of what you're being interested in. But again, this can sometimes not be done. So you will also discuss instrumental variables. You will talk about mediators in other classes. But yeah, it's important that you know what you're adjusting for, when you're adjusting for something, and what you're actually doing with that powerful tool of R that you have at your hand, because you can do a million things and you need to really understand what you're doing. Okay. All right, if any question on that, please post on the discussion board, but I really refer you here to also to your epidemiology books. You must have had your first classes of epidemiology already, so you have probably already quite clear idea about some of the things that I've been telling you today, but please read up on it. It's very important knowledge. Very important to keep in mind also when developing research questions, when studying research questions, and when designing analytic approaches. So the research note 1 that is being assigned today, we are being asked to perform an investigation using R on a subset of the NHANES. We are proposing a research question which consists of an outcome using variable Y, a study variable X that is likely to affect Y, a list of potential confounders that you're interested in, and then I would ask you to conduct unadjusted and adjusted analyses. For these analyses, I would please also ask you to perform model diagnoses to make sure that we are really on the same page and that we really know what we're looking at. And lastly, I would like you to write up a brief report, which should have, you give me at least like 2-3 sentences of introduction, a little thesis statement, brief methods, a result section, and then some concluding remarks. It doesn't have to be long. It doesn't have to be crazy long. The specifications you will see in the assignment, but just let's make this kind of a sound kind of piece of work. I would really ask you for that. All right, sounds good. Okay, so I'm looking forward to your entries on the discussion board, and good luck with the research notes, and looking forward to reading your ideas. All right, bye-bye. Oh, at lab 7. Yes, also with the exam 1, I say it again, exam 1 will go online on 10/18 at midnight and will be online until 10/23. So this is online for the entire week and you can take it at any time. Keep in mind that it would be very good if you would really prepare yourself for that, but it should be super easy. Particularly pay attention to homework 1. All right, good luck.